Here's a problem that's available for you on the Blackboard site. It's from section 2.9 dealing with the dot product. What we have here is a pole that extends from the origin to point A, and at point A we have a 600-pound force that's pointing off into space. And what the problem is asking us to find are the components of the force that are acting parallel and perpendicular to the axis of the pole itself. So let's try and understand what it is this problem is asking for. I can draw a line that passes through O and through A and extends into infinity in both directions. There's no reason why I can't take this line and draw it longer than the pole itself. Now this is just a line, it lives in space, but we can visualize it here, but it has no other meaning except it just happens to coincide with the pole itself. What the problem is asking us to do is to consider this 600-pound force and to recognize that this force does in fact have a component that is pointing along that line. We could project that force along the line, and we could call that F parallel. And there happens to be a perpendicular component to that first component we drew that would be called F perpendicular, perpendicular to that line. And although this doesn't look like a right angle because we're drawing 3 dimensions in a 2-dimensional space, that is in fact a right triangle or a right angle between F parallel and F perpendicular. Okay? So we're considering a 3-dimensional space now. We're just increasing by 1 dimension from what we've done up to this point in class. But otherwise, this is no different from what we've seen before. In the past, when we were considering coplanar forces, we'd have maybe an x-axis to the right and a y-axis to the left, and I could draw any vector in a particular direction. Consider this vector A, like so. Well, I know from experience that this vector A has a component along the x-axis that looks like this, and it has a component along the y-axis that looks like this. Recognize that the x component of my A vector is pretty much what I just drew for F parallel over here. And A sub y is no different than F perpendicular. If I were to give you an angle theta, then you would know immediately how to solve for A sub x. A sub x is simply the magnitude of A times cosine theta. Okay, well, what we also find out is that A sub x, another way to write this, is you take the vector A and you dot it with a unit vector which describes the direction of the line you want to project your vector onto. So if I were to come up with a unit vector that's pointing in the x direction, then I would just simply need to take the dot product with my vector A and the unit vector, and I will come up with the same answer as I had before up above, up here. Let's see how that works. Well, it says A sub x is equal to the dot product of A and the unit vector. The dot product is defined as the magnitude of your first vector times the magnitude of your second vector times the cosine of the angle between those two vectors. That is exactly what we had written up above. What's nice about the dot product is this is a more general way of determining it's a more general expression that describes how you can determine the magnitude of a component of a vector along any line in space. Okay? As long as you can determine a unit vector describing that line in space, and you know the vector itself that you want to project, simply taking the dot product of those two vectors will give you a number, and that number corresponds to the magnitude of the component of your vector along that line in space. Okay, considering that, let's look at what the plan of action is for this particular problem. We want to determine the force in terms of I, J, and K components. That makes sense. That's analogous to our vector A that we've included up here. We want to determine a position vector from the origin to A. And with that position vector, we can then determine a unit vector that describes the direction from O 2a. This is the unit vector that we want to use in our dot product. So once we dot F and the unit vector from O to A, we will uncover the component of the force that is along the line OA. Okay, well here's something. Let's go back to this two-dimensional picture. This is a right triangle. If the hypotenuse, the length, is equal to the magnitude of the vector A, then I can use Pythagorean theorem, A squared is equal to A parallel squared, or rather AX for this drawing, sorry, plus AY squared. And I can solve for AY, which at this point would be the only unknown in this equation. A squared minus AX squared. This is how I can solve for the perpendicular component. I solve for the parallel component using the dot product. I solve for the perpendicular component with Pythagorean theorem. This is a right triangle over here in 3 dimensions. So I can use Pythagorean theorem to solve for my perpendicular component. That's what step 3 is telling us to do. Now that we have the plan, now that we understand the plan, let's just start working through this and get an answer already. Okay, first thing we need to do is determine our force in terms of components. So our force we want in terms of I hat, J hat, and K hat quantities. So if I'm going to determine the I hat, I need to take the magnitude, 600 pounds. I'm going to project it down onto the XY plane, or parallel to the XY plane, by taking the cosine of 60 degrees. That gives me the length of that line, this black line that I've shaded in here. But I only care about the component that is in the X direction. So I'm going to take this and multiply it times sine of 30 degrees, which would be the length of this side of the triangle, which is parallel to the x-axis. Don't forget, I need to put a negative sign there because it's pointing in the negative I hat direction. So I put an I hat there and a negative out front. And then add to that 600, again, cosine 60, and this time I want to take the cosine of 30 degrees because that will give me this length of the triangle, J hat. And this 600-pound force is pointing upward, so that's going to be plus 600 sine 60 degrees, K hat. I'm going to put brackets around this, put pound force at the end to remind ourselves of the units. There we go. First vector done. All right, that was the first step we needed to do, was find the force. The second thing we need to do is define a position vector from O to A. So R from O to A is equal to what? Well, I'm starting here. So along the x-axis, I would need to go negative 4 I hat feet. I would then need to walk down the y-axis 4 feet plus 4 j hat, so in the positive y hat direction. And I would also need to go up, so in the positive z direction, 2 feet plus 2 k hat. Brackets around this, put feet. If I want to determine the unit vector from O to A, because if I go back to this first slide again, I've just determined my position vector from O to A. Now I want to determine the unit vector from O to A. This is just simply the position vector from O to A divided by the magnitude of that position vector. This guarantees that the vector has a magnitude of 1 and has no units associated with it. It's only there to show dimension. So this would be equal to negative 4 I hat plus 4 j hat plus 2 k hat. Carry around the units if we want it, divided by the magnitude of the position vector. This will be 4 squared plus 4 squared plus 2 squared. 16 plus 16, 32, plus 4 is 36. Square root of 36 is 6. So everything here is going to be divided by 6. So negative 4 over 6 I hat plus 4 over 6 j hat plus 2 over 6 k hat There are no units associated with a unit vector. This had dimensions of feet in the denominator as well. If you take the magnitude of this vector, you ought to find that the magnitude is equal to 1. I'll let you do that on your own. We have finished step 1. Last thing to do is determine the parallel components of f using the dot product, because the reasoning I had laid out from before. So simply take the dot product of f with the unit vector that describes the direction of the line you want to project onto. So f parallel is going to be equal to f dotted with UOA. Notice that this term here, the parallel component, does not have an arrow over it. When you take the dot product, you punch in two vectors, you come out with one scalar. So I'm going to reduce this. I'm going to punch this into my calculator. The force here is negative 600 times cosine 60 times sine of 30. That's going to be equal to negative 150 I hat. I have 600 times cosine 60 times cosine 30. That's plus 259.8 j hat. 600 times sine of 60 is plus 519.6 k hat. That's when I reduce my force vector from above. I'm going to dot that with my unit vector. If I reduce this, it's going to be negative 2/3 I hat. It's going to be plus 2/3 j hat. This is going to be plus 1/3 k hat. When you take the dot product, you multiply the I hat terms together. Then you add to that the product of the j hat terms. Then you add to that the product of the k hat terms. So f parallel is equal to negative 150, don't forget the signs, times negative 2/3 plus 259.8 times 2/3 plus 519.6 times 1/3. There are no I hats, j hats, or k hats in this equation. The dot product does not yield a vector, so you only get numbers. So negative 150 times negative 2 divided by 3 plus 259.8 times 2 divided by 3 plus 519.6 divided by 3. I get 446.4. The units here are going to be in pound force. That's my component parallel to the axis OA, or the line OA. That's this one. What did I say it was? 446.4. 446.4. The length of this line corresponds to 600 pounds. Now all I have to determine is my perpendicular component. We said that this is a right triangle, so I only need to use Pythagorean theorem to get there. So f perpendicular is going to be equal to the square root of f squared minus f parallel squared. This is going to be equal to 600 squared minus 446.4 squared. 600 squared minus 446.4 squared. Square root of that. It's equal to 400.9. So 401 pound force. That is the perpendicular component. And here we have the parallel